Welcome once again, viewers, to Juddy Productions. In today's video, we'll be looking at how is motion understood, focusing on the topic of energy conservation, and we'll be looking at energy system calculations. An example. So you see on the screen at the moment we have a cart running on a section of roller coaster track, and we have 3 questions to answer. So let's jump straight to it. Our scenario is as follows. A roller coaster cart with a mass of 1 ton is moving along a horizontal section of the track at a speed of 5 meters per second, as shown below. Point X is at the edge of the horizontal section of the track and has a height of 10 meters. Point Y is the lowest point of the track. The track is designed so that the roller coaster cart will come to rest at point Z. Ignore the effects of friction. Task number 1. What is the kinetic energy of the roller coaster cart at point X? So at point X, we're asked to calculate the kinetic energy. We've been given the mass of the cart as 1 ton, which we know to be 1,000 kilograms, and the speed of the cart at point X is 5 meters per second. Kinetic energy has the following equation: EK equals a half mv squared, and we substitute our values in, where the mass was 1,000 kilograms and the speed was 5 meters per second. That gives us a kinetic energy of 12,500 joules, a relatively simple calculation. Task number 2. What is the speed of the cart at point Y? Task number 2 requires the understanding that the sum of the energy within this roller coaster track is the same at all points. That is, the total or the sum of the energy at point X will be the same as the total or the sum of the energy at point Y and that of point Z and all other points in between. That is to say that energy is conserved. We can't create it or destroy it. So at point X, the total or the sum of the energy is the sum of the kinetic energy at point X and the gravitational potential energy at point X. And we can calculate that using the half mv squared for kinetic and the mg delta h for the gravitational potential energy. We sub in our values and we find that the total amount of energy, or the sum of all energies at point X, is 110,500 joules. That means that anywhere in this system, the sum or total energy of this cart will be 110,500 joules. It just changes its form from kinetic to gravitational potential along this particular journey. So let's have a look at this particular question where we're asked to find the speed of the cart at point Y. So we know that the sum or the total energy of this system at point X will also equal the sum or the total energy at point Y. So the sum of the energy at point Y is equal to the sum of the kinetic energy at point Y and the gravitational potential energy at point Y. And as you know, that's equal to half mv squared plus mg delta h. Now note that the v and the delta h at point Y in red, seen on the screen, is different to the g and the delta h at point X as seen on the screen. So at point Y, the kinetic energy is equal to 1/2 of the mass, that is 1,000 kilograms, multiplied by the speed squared, the unknown value for v. And the gravitational potential energy at point Y is equal to 1,000 times 9.8 times 0, because our heights are measured relative to the ground, and at point Y, the track is on the ground. This effectively means that there is no gravitational potential energy. So the total energy anywhere in the system is equal to 110,500 joules. At position Y, that equates to 500 times v squared. We now want to work out what is v, the speed of the system. So we divide both sides by 500 and then take the square root, giving us a speed at point Y of 14.9 meters per second. Again, a relatively simple calculation, given the understanding that the total or the sum of the energy anywhere in the system is equal. Task number 3. What is the vertical height h of point Z above point Y? So we want to calculate the height of the cart above the ground at point Z, recalling from our initial description that at point Z the cart has no speed. So once again, the energy is conserved everywhere in this system. And so the total energy, or the sum of the energy at position X, will be equal to the sum of the energy at position Z. At position X again, we know it's the sum of the kinetic energy and the gravitational potential. And we've calculated that previously to be 110,500 joules. This time we're investigating and we're interested in position Z. So of course, the total energy is the same also at position Z, and that consists of the kinetic energy at position Z and the gravitational potential energy at position Z. So there's a half mv squared for the kinetic energy at position Z and mg delta h for the gravitational potential energy at position Z. So the kinetic energy is a half times the mass per 1,000 times of speed of 0 squared. There is no speed at position Z, and so, accordingly, there's no kinetic energy. all we have present in terms of energy really is the gravitational potential, which is equal to the product of 1000 times the gravitational field strength on Earth of 9.8 times h, the height or the elevation above the ground. That can be simplified to 9,800 times h. Of course, we divide the 9,800 across the left-hand side, and we're left with a height of 11.3 meters. This is the final task in this video, and it once again demonstrates the application of the conservation of energy in a system, allowing us to work out either speeds or elevation heights given the total energy from a reference point. I hope this video has demonstrated a systematic approach to calculating unknown variables from a constant energy calculation. Thanks for watching.